We have been investigating the magnetic field. We've looked at it in terms of its source, that is, currents, moving charges. We've looked at it in certain situations like simple geometries, such as a long straight wire or a curved wire, and we've seen formulas for determining the magnetic force exerted on current carrying wires. We started out the discussion with magnetic forces on charged particles. What we haven't done, though, is come up with a general formula to determine the magnetic field at any point in space due to any current carrying wire. To do that, though, let me remind you of something that we've done quite often. The equation for the electric field in vector form. Normally I would write here K, the Coulomb constant, but for reasons which I hope will become apparent in just a second, I'm going to write out what K is. It's just a bunch of constants. 4 pi takes care of some of the geometry, epsilon naught is the vacuum permittivity, and then times Q, the source, over R squared, where R is the distance from the source to the observation point, right? I'm looking for the field at some point. I have a charge somewhere, and I'm looking for the field at all the other points. So this distance is the distance between the charge and wherever I happen to be looking. And then to ensure that this is a vector equation, I need to tack on the distance, the direction, where r hat is a unit vector that points along the line of r, which is r would be the displacement between the source charge and the point of observation. This is not a displacement, of course, because I'm squaring it, but r hat points along that line between Q and my observation point. So we've seen this, we know how to handle it. We've directly integrated this when we were trying to determine the electric field due to some charge distribution. How did we do that? Remember, we formed this in differential form. We said that if I take a continuous charge distribution and take one little element of it, then I have a dq instead of a q. That dq contributes a little bit to the field, some dE, and then I integrate to add it all up. But if I did that, I got 1 over 4 pi epsilon naught dq over r squared r hat. And generally I didn't deal with the vector nature of this when I was integrating. I would deal with magnitudes and then come back and put in the vector nature by inspection. So this was the general way I proceeded. The Coulomb equation here for fields and then in differential form. Well, I can do something similar for magnetism. So let me introduce you to what's called the Biot-Savart law. I'm going to just write this in differential form because, as it turns out, you're probably never going to use this unless you are actually going to integrate. But it works very similarly. The magnetic field contribution due to some small element of current. We have dq for charge. We're going to have some di for current. I'm going to write it a little bit differently and then show you how it got to what I'm going to write down. But I have some current element that contributes a little bit to the magnetic field, just like I had some charge element that contributed to the electric field. So this is going to be mu naught over 4 pi and times I dl cross r hat over r squared. So first, let's take care of the constants over here. There's some similarities here. I've got a 1 over 4 pi, I've got a 1 over 4 pi. As you can probably imagine, this comes out of the geometry. The difference is my constant. The electrical constant is epsilon naught, the vacuum permittivity of free space. This is called the magnetic permeability, mu naught. In case you're interested, mu naught has a value of 4 pi times 10 to the negative 7th Tesla times meters per ampere. The units are strange, right? We figure out the units that it's going to take to make the constants work when we determine the constants, and that's where that comes from. Interestingly enough, though, this is a nice, pretty number. It's irrational, of course, but remember, the vacuum permittivity had a lot of decimal places. This does too, but they're wrapped up in pi's. That's really an interesting result. But mu naught over 4 pi is the constant here. And then I've got the source, right? Just like I had the source here, but I didn't write di. I wrote dl, and we'll talk about that in just a second. And then cross r hat. R hat is again going to be a unit vector that points along the line from the source, that is this current element, to the observation point. And r squared, of course, is the distance from this source to the observation point. And so if I have some wire carrying a current like this, here is my current element. Here's my observation point. Get a different color. The vector current, this IDL, and we are going to talk about it, looks something like this at that point, right? For this little differential element, I'm going to be tangent to any curve that I have there. And then, looks like the r hat is going to go something like this. So that's r hat, where it points along the line, that is r. This would be dl. And the current is being carried by the wire, which is I. So as it turns out, writing di is okay. You can write the current element di, but you have to put this in vector form. Why in vector form? Well, we have seen that the magnetic field has these really interesting property of being orthogonal to the current and the magnetic field. It has to be mutually perpendicular. And so the way I'm going to have to characterize that is with a cross product. So I need the current to be a vector, and that's fine. You can make anything a vector you want to. As it turns out though, if I say that I is a vector, that's fine, but notice that that vector, at least in this case, is changing constantly in direction. But I is a steady current. So I could do that, but to be more facile, it's usually easier to express this di as which includes the current and the direction, right? The current would be the magnitude here, as the magnitude times dl, where dl is the actual path. And so dl in every case is a little bitty path element. So I'm going to integrate along a certain path. I have to integrate along a path because that's where the current is. Just like for this, I had to integrate along the charge distribution. If it was a rod, I had to integrate along the rod. If it was a ring, I had to integrate around the ring. If it was a disc, I had to integrate over the surface of the disc. That's where the charge is. Well, this is where the current is. So I've got to integrate over this path. The best way to characterize that is to not write di. It's to write I, the magnitude, times dl, the differential path length, the differential element along this path over which I'm going to be integrating. Of course, if I write this angle is theta, which will come into play with my cross product, which is defined in terms of the sine of the angle between them. You can also get directions by the right-hand rule here. So we're going to see in future videos a few examples of how to deal with this. Of course, I should point out, to determine the magnetic field, I just integrate, right? I integrate over dB, just gives me just gives me B, and then I integrate over the path, and this will give me the functional form of the magnetic field. We're going to see a few examples in future videos of how to do that in a couple different geometries, but let me say a couple things about this. This is not as easy to deal with as the electric field, and that's because of this cross product. So recall that this cross product is going to produce a vector. This is what makes it a little bit different. My normal strategy with anything involving electric field, be it something like this or be it Gauss's law, which has a dot product under the integral, was to take care of the calculus and then get whatever I could out of the integral. Remember in the dot product, or in Gauss's law where I used the dot product, I used Gauss's law in situations where that dot product turned out to be something constant that I could take out of the integral. I'm going to try to do the same thing here. It is not always possible to do that, however. It depends on your coordinate system. If I'm in Cartesian coordinates, and I'm going along, say, a straight line. This turns out to be really easy. Let's say I'm moving across the x-axis, then this just becomes a dx, or some x dx, and this would be something a little bit more complicated because I'm observing at one point. And that might be okay, but if I'm dealing with spherical coordinates or cylindrical coordinates, there's no guarantee that the product of this will be a constant. Remember, if you're in spherical coordinates, theta hat and phi hat are not constants. So I can't, even though they're unit vectors, they're constant in magnitude but not in direction, so I can't just pull them out of the integral. So we're going to have to be careful with how we handle this, whether or not, and we're going to have to be really clever with what we can pull out of the integral because it's constant and what we can't because it's constant. So more examples to come.